Optics. I basically want you to be able to recognize a couple basic lenses and the ray diagrams for them. So here, for example, is a diagram of a person staring at an object. Object out here, the ray diagram places the image right here. But this image should be on your retina to be seen. So we need to adjust this person's vision to get the image here onto that retina. So the question is, what would you do with these beams of light? Spread them apart so that the intersection moves back here, or bring them in even closer to move the intersection back here? Once you make that decision, which one of these lenses would adjust the rays of light to go in the correct direction? So if you take the eyeball away, you can sort of see this. Do we want to widen these rays so this point goes to here, or do we want to bring them in tighter? And the answer would be we want to widen them. If I take this ray here, for example, and tip it up, and take this ray and tip it down, the intersection will move back. Well, which lens does that? The convex lens it's bowed out, or the concave lens it's bowed in? So this person needed these lenses to go here. Now, what if they couldn't afford glasses? Would they want to walk closer to this person or back away? And the answer is they would walk closer, because lenses do the opposite of mirrors. When you walk closer to a mirror, your image gets closer. But when you walk closer to a lens, the image backs away. So this guy would walk closer to the target to see him. So he's nearsighted. If he doesn't want to have to do that, he needs these lenses to spread the beams. Now, what about this one? This person here is standing here. I forgot to put the lens in their eyeball like the spot, but here's the lens. And the image is forming way the heck back here, and there's the retina. So does this guy, do we want to bend the rays in more to bring the image here, or do we need to spread these rays out? And the answer is we need to bend these rays so they come together quicker and actually land here. So it would be the convex lens. So this person needs to wear this lens to see up close. Now, what if he couldn't afford glasses? What would he do? Well, if he asked this thing to back up, then the image would come forward. So you get further away from this image to bring the object in closer. So this means you don't see well when something is close, you hold it farther back. So you're farsighted. And that's what Granddad does with his book. If he doesn't have his glasses, he has to hold his book farther away from his face. So Bubbles is farsighted. He needs these glasses to see things up close because they're magnifying lenses, because his eyes are bigger. But he doesn't wear these when he's reading. He's wearing them when he's walking around. So Bubbles is deliberately wearing the wrong glasses for comic effect. Everything would be a blur at a distance. If you're wearing glasses to see at up close, if you're wearing glasses to see up close, they're these kinds. If you're wearing them to see far away, there's these kinds. Even myself, I get a little bit tired there. Now, these curved mirrors will take parallel rays, send them through the focus. So they'll set fire to something. And it doesn't matter what you use. You can use sound, light, rain. We can collect radio waves from outer space. They come in parallel, go through the focus. In World War II, they could do the opposite. You put something at the focus and the lights come out straight, you make a spotlight. So they're projecting the bat signal onto the clouds. If you put two of these things together, you got a great two-way communication. This satellite sends a beam towards the reflector and it leaves parallel and it's shrinking because it's going far, far away. And then when it hits the satellite's dish, the satellite recollects it at a point and listens. And when the satellite's ready to communicate to Earth, it fires its own beam backwards at its own antenna, and then it reflects and comes out nice and straight and reassembles on Earth. This allows us to transmit Like these satellites are beyond Pluto, and their transmitter is no more powerful than a police walkie-talkie. Here's another graphic illustrating the same thing. If you leave a bulb out exposed, the energy spreads out real fast and gets real dim. If you got 10 times further away from this light bulb, it would be 100 times dimmer. But if you put a reflector behind the light bulb, you can make everything come out parallel and the spot stays bright for a long distance. And we call it spotlight. Now, if you took that spotlight and you aimed it at another reflector, it would actually reconcentrate the light just as bright as it was in the bulb. And you could do that across the length of the whole school. And you could also set fire to things that way. If I was mean, and I would love to do this one day, build a big 6-foot mirror, you could start a fire at the focus of the 6-foot mirror, and out on Murray's Mountain, you could place another mirror and you could toast hot dogs at that focus exactly like you were above the campfire. So that's the part of optics I want you to know. Biology, what do I really need you to know? Know that that's the nucleus. Know that the mitochondria has energy, okay? And know there's a vacuole to pitch out garbage. That's really all I need you to know. And any terms I need will be given to you. So Ken, if I say which part of the cell does the thinking, nucleus or vacuole? Could you tell those two apart? Kinds of cells, not all this. Muscle cells are stretchy. They have big mitochondria for energy. Nerve cells are long like wires. And blood cells, we've got red blood cells that are scooped out to carry oxygen. We've got coconut sprinkled Timbits, white blood cells that fight invaders. And those are their little probes as they go around feeling the body. And then there's these balls of snot kicking around here. And those are your platelets. And the platelets seal up cuts. That's it. That's all you need to know about cells. Then we get to this part here, the circulatory system. We have blood goes to the lungs. It's blue. Why? There's no oxygen in it. The blood turns red. Why? There's oxygen. And it got rid of CO2. It goes to the heart, and the heart goes poof and blasts it out. Now it's under pressure. It takes the oxygen to the body. The body uses up the oxygen. It goes back to the heart. Okay? And then the heart goes poof and back to the lung. Oxygen goes in, CO2 goes out. The lung part is called pulmonary. The body part is called systemic. Then the heart actually has its own blood supply on top. Just as it leaves the heart here, there's a little sneaky branch, and the blood goes flying out and covers the heart itself. This left anterior descending, that's where my heart attack was, right about there, about the worst spot possible. If my heart attack had not been treated with it blocked right there, the entire left half of my heart would have died, and you'd have a supply teacher. And they'd be like, yay! But you wouldn't know. You'd just be like, well, I got here because some other teacher died. So if you don't like me, you can curse the doctor that fixed that spot. Cell division is called mitosis. Mitosis are cold. I didn't wear thick enough socks. You perform mitosis when you grow, replace, or repair cells. Obviously, you spend a lot of your life in mitosis as you grow up. Then you only go into mitosis to repair or replace stuff that is worn out. And even that gets reluctant. Look at my beard. It's gone white because my body's like, oh, I can't be bothered to repair the color. Your cells are supposed to know when they are finished and stop mitosis. But sometimes they mutate and they get stuck in a copy-making fever and forever and forever and forever, and they grow rapidly to form a tumor. So the key point is they get stuck in mitosis. They go crazy. They start to mutate and don't do their original job. Like there's a tumor and it's on your fingernail, and it suddenly goes, I'm going to make a tooth and I'm going to make some hair. And it just like, you're like, what is it doing? And then the tumor falls apart like dandelions and they spread elsewhere. They can even command the body like, you must feed me. And your body just starts routing all the food to the tumor and you begin to lose weight. So we really got to stop them from doing this. And so I like to think of the tumors as these. A benign tumor can still kill you, but it's growing like this smooth egg. So it's in your brain, but it's just like pushing the brain out of the way. And so if they can go in, they can sort of just like